when we were looking at those simplifications that can be done, one of those simplifications involved an infinite plane of charge, whereas a surface charge density, eta. Now, how can that be useful? Well, in the same way that we took that line of charge and said, you know what, if we're really close to a line of charge, let's just treat that as infinite. It makes the math easier. Let's say that I'm looking at a case where I've got a disk of charge in the xy plane with the charge Q over an area A. Now, we can calculate that out to work as, hey, a disk. We have the equation for that. We know that if we're very close to that disk, we can have that work as an infinite plane if we're really close to the disk. But suppose then, on a large scale, that's not helpful to us. But suppose that I've got a disk of charge with a total charge Q. Now, some separation d away, I've got another disk of charge, and here, that has a total charge of negative Q. If and only if d, the separation between the two, is way less than, the length of one side, call it the square root of an area, then in the space between it, for every space, maybe not at the very end, but for most other spaces, I can say, you know what, let's just treat this as looking at two infinite planes. Here's why that's helpful. Because if I have this positive charge, the positively charged plane Q is going to give me electric field lines radiating outward from the positive plane in both directions, honestly, these lengths should all be constant because the magnitude of the electric field will be eta divided by a constant, 2 epsilon naught, where eta is the charge over the area. Now, if I draw the electric field lines for this negative charge, they are going to be radially inward. And this is the clever bit, because Well, these will have an electric field strength of eta, the same charge over the same area, divided by 2 epsilon naught. So these will have the same magnitude, which means that in any area not between those two plates, if the two fields are pointing in opposite directions, they're going to cancel each other out. Sure, I'm a little bit farther away from the positive plate than I am from the negative plate, but I'm treating those as infinite planes. So distance, the field doesn't depend on distance. In the same way on the other side, hey, they're in opposite directions, they cancel each other out. So if I look at this case here, I have an electric field of 0. Here I have an electric field of magnitude 0. And in the middle, I have an electric field with a magnitude of 2 times eta over 2 epsilon naught, or just eta over epsilon naught. And that's good because if I make 2 large planes of charge, 2 large plates, and this stores charge, as we'll see in the future, so I can simply build a parallel plate capacitor, store positive charge on one plate, negative charge on the other, and that means the electric field between them is basically constant, which means we can do experiments in a constant electric field by making either a small experiment or a big capacitor. This is the value of the capacitor.